Hey Ryan, can you hear me?
Yeah, I can hear you.
Okay, good. Yeah, hi everybody. I'll wait for a few more moments until the clock before we start. Um, can you guys all hear me? Can send up a chat um, or thumbs up and let me know if you can hear. Okay, so we'll get started. And it look like we have quite a few online, and I'm gonna record the lecture, and I'll post it for those who are not able to join online. As I said last week, we're gonna be spending 2 lectures, which is this week on operation amplifier circuits. And next week, on Monday, we're gonna do a review of the whole class and connect the dots. On Wednesday next week, we're gonna have really pretty much open office hours most of the day, and Thursday as well. And then Friday we'll have the final exam. So I know for some of the students, if you need the accommodation of exam, you need to contact the testing center to make that schedule ahead of time. So let's dive into the contents for today. Well, the idea that we study the operation amplifier in this chapter is that now so far we have studied, of course, we're going to do this review as well next week, about amplifiers, and we studied the small signal circuits, the BJT MOSFETs, the small signal circuits. And then in chapter 7, we discussed the simple amplifiers like single stage, single transistor amplifier. And then in chapter 8, we talk about the building blocks, basically looking at again different types of amplifiers. And then we talk about the current mirrors, current steering circuits, and the cascade, and the current mirror loads, things like that. And then in chapter 9, we talk about multi-stage and differential amplifiers. That's what we're going to also partially cover today. And then move on, we talk about frequency response. Then we talk about feedback. And then we talk about the output stages and power amplifiers. In this chapter, we're really putting things together to look at the 2-stage op-amp. And there are a few other op-amps discussed in this chapter. Given the time constraints, we're not going to be able to talk everything. So we're going to only talk about CMOS 2-stage, which is section 1 of chapter 13. But what this does is that give you idea of what the op-amp would look like, or what a generic amplifier would look like. And if you needed more information, if you need a different type of amplifier, you certainly will be able to do that. So let's dive into this simple CMOS 2-stage amplifier that we'll be discussing for today and Wednesday. Look at the circuit in front of you. You can see that this circuit is a 2-stage, and it has a differential input, and it gets a single output. So what does that? The unique characteristics of this amplifier that let's see. Hold on, something happened with my pen. It doesn't work anymore, so I probably need to just give me 1 second. I need to. It was working just a little while ago. Not sure what happened. Okay, let's do this. Nice. So add. Yeah, it's 100% charge. Okay, it's connected. Okay, let's go back to our presentations. Hopefully it will work this time. Yeah. So the unique aspect of this amplifier is that it is a 2-stage. Now, we want to discover the stages. If you look at the circuit, apparently where it marks the input minus, that's your input. So that's your input minus input. We can call it I minus, and this VI plus. The output of your first stage is at the drain here. So that's your VO1. And that output is connected to, or here, it's connected to the second stage, which is here. This one, Q6, is your second stage. And as you can see here, you get output of VO at the drain of Q6. So the two stage, which basically said that stage one is composed of Q1 and Q2. So that's your first stage. And your stage 2 is composed by Q6. So this is your stage 2, and this is your stage 1. So now we identify these two stages. There is a CC capacitor, and we're going to talk about the function of CC later. As you know, probably from chapter 10 and 11, you know that this is the feedback. But why use the CC feedback? Because we want to use that to increase the frequency response, improve the frequency response. So that's why we need the CC. But we're going to talk more about it on Wednesday. So today we're going to just leave it like that. Another unique characteristic is that this amplifier has two stages. So it does not have an output stage. If you want to have output stage, we would simply add something like here. Remember the different output stages that we can do? That you can add, for example, you can add a BJT here to form this class, different class amplifiers, class A, B, and C. But over here, we don't have output stage, so we will simply neglect that. Okay. So moving on, that you might say, okay, it is a two-stage amplifier. I know now Q1 and Q2 form the differential stage, the first stage, and Q6 forms the second stage, and CC forms a feedback which is increased to improve the performance of the amplifier, frequency response performance of the amplifier. But why are we having so many other transistors? Well, that's something that we need really to identify in this application. Oops. What happened? Sure. So we need to interesting. Okay. So we need to identify the function of other transistors. For something the slide is not spinning, so let me redo. Sorry about that. Okay, so now we should be able to go to the next slide. Well, we already identified Q1, Q2, and Q6 as amplifiers. So if you look at the other circuit here, you probably already noticed that, well, we have a current source. Well, here, if you look at here, what happens here? That is a current mirror. The current mirror is formed by Q8 and Q5. Okay. In addition to that, actually, if you look at Q7, the gate of Q7 is also connected gate of Q8. So therefore, Q7 is also a current mirror. Q5 and Q7, they form current mirror. So when this happens, you have a current of I through Q5 and Q7. Now, of course, here we assume that Q8, 5, and 7 are matched. So if they are matched, you actually would have the same current in this. However, I want to erase this one because we'll talk about Q7 later. Q7 is not going to be matched. Actually, it's going to be twice. The reason is this. If you look at a current, through Q5, when the current goes through Q5, it was split between Q1 and Q2. So you've got IQ1 and IQ2, each is going to be 1/2 I. right? So therefore, what do you want to do in Q6? Is this really where you want to see whether you want like bias as I, or you want to bias at 1/2 I, or you want to bias at 2I, whatever, that is going to be. So that determines the Q7 may or may not be matched. So now we identified the current mirrors. Well, in the current mirror, we also have a current source, R reference. This R reference can be another, the current mirror or current source that you build. It can actually be replaced by a simply just a resistance. If you look resistance here, and you basically can create this current value right away. So we're going to put Q7 to be determined. Yeah. So now we identify all this. So Q5 and Q7, they're current mirrors. Q8 is the steering circuit, and Q6 amplifier, Q1, Q2 amplifiers. And beyond that, we also have a resistance of Q3 and Q4. Now, if you look at the way that Q3 and Q4 are connected, they do like the current mirrors, but they don't have a steering circuit, which means they look kind of current mirror, but they don't have current. So what we call this? Remember from chapter 8, we call this current mirror loads. So Q3 and Q4 is current mirror loads. This is very important because what they're doing is, so if you look Q3 and Q4, they look like this. They look at current source, and then they have a resistance like RO3, or the other one will be you have I, this is 1/2 I, which conducts from there, and you have RO4. So identify this one. Now, in the meantime, Q7 is a current source, a current mirror. In the meantime, Q7 can also represented by a current source with in parallel with its early resistance. So therefore, if you want to replace this whole circuit, we actually have a simple way to replace it. And but here, let me actually look at the circuit. Is that what we need to do is we want Q6 to Q4, Q6 and Q4, yeah. So Q6 is the transistor over here, Q4 is over here. So that the ratio between Q6 and Q4 should be twice as 7 and 5 in the area. Why? Because if this conduct current of I, the current in Q1 and Q3, as well as the current in Q2 and Q4 are going to be 1/2 I. But if Q7 matches with Q5, you're going to provide I. And if you provide I, what it means that the Q6 current is I, but Q4 current is 1/2 I. So if you compare these two, the area of Q6 should be twice of the area of Q4. So this is what we are saying is omega L of Q6 should be twice of the area of Q4. So that's why this equation comes from. So YOL of 6 over YL 4 should be twice as WOL 7 of WOL 3. So now we have all the components identified. What we need to do is I want to rewrite this one, is area of, oops, oh, this is not good. I simply, okay, cancel. I just lost the, it's okay. I guess I can quickly go back to to circle. So the components, as we do this amplify, we identify amplify, then we identify Q8, Q5, Q7 are current mirrors. Okay, and then we also identified Q3 and Q4 loads, and Q7 is also a load. Okay, so this load and this current mirror, and these are loads. And there we have identified, okay, and we also have identified why area of Q6, WOL of Q6 should be twice as WOL of Q4. Just conduct, because the current is half I, half I, half I, half I, but current here is I. Okay, so that's where we. Now let me go back one slide. Is that now we have identified all the functions and components, we can simplify the circuit, because in the first stage, you have a current source, okay, and then at the bottom you also have current source, but this really is just a current mirror load. That's your first stage, and here, oops. So this is your first stage. You have current load and you have input. And your input is basically at the gate of Q1, Q3. And here at bottom, we can connect them. And the second stage goes from your amplifier here and it goes to Q6. Let's for now neglect the CC to look at. So the 6 will be looking like this. And you have Q7 also has resistance, and this is your ground, and this is your output with O. So I want to identify a few things here. Now, this one here, of course, is a PMOS, and this is PMOS, and this is NMOS. So over here, the resistance here can be neglected because this is at the source. So this, the first stage is common source. So the resistance as a source can be basically neglected because eventually they look like a short circuit. And here you have 1/2 I, and you have RO2, RO3, and you have RO4. So remember, again, here we neglect resistance for RO8, RO5 because now I actually split this one to 1/2 I, and then altogether they really should be just I. Okay, so here as a stage we have RO7, which is current resistance of the current mirror, and we have output of VO, and this is also a common source amplifier. So in a little bit, we're going to look at the equivalence, small signal equivalent circuit, and then we're going to derive the gains. But before that, let me talk about the input range. So when we talk about input range, we are going to talk about the input common mode. So if you look at Q1 and Q2, so what happens when VCM, I think in the book it's called VICM, as input common range. If VCM is too high, what happens? We can say if VCM is too high. If VCM is too high, you can see that if VCM is such high that it exceeds, let's call this VD5. Then VD5. Then what happens is that this transistor Q1 is going to be not in saturation. It's going to be in cutoff or tri mode, not in saturation. So therefore, it will stop functioning as an amplifier. Therefore, VCM has to be lower for the upper limit. Now we're talking, it has to be lower than a certain value. Well, how low? is that we need to say that what we can say is we from here. So this is D, this S. So typically, for PMOS, we can do the absolute value instead of the actual value. So VDS has to be larger than VOV, which is so let's make sure that we got the right convention. So first of all, Q5 has to be in saturation as well. If Q5 lost saturation, we lose current source. Overall, the circuit will also not work. So over here, let's start with Q5. So Q5 VDS, let's call VDS5, has to be larger than VOV5. And in order to have for Q1 for Q5 in saturation. Now we know that VDS5 equal to VDD minus VD5. So therefore, and this has to be larger than VOV5. So therefore, we have from this equation here, so we have VD5 has to be larger than VDD minus VOV5. So the first one, we got this one here. So VD5 has to be larger than VDD minus VOV5. But then now we already said that Q1 also has to be a saturation. So therefore, if we look at this one here, Q1. So Q1 between source and input, the voltage from its source to its gate can be expressed as VGS1. Let's use again absolute value. It's going to be VD5 minus VCM. Okay, so that's now we can say that from here that we can say VCM equal to VD5 minus VGS1. We got this value. And VD5, we already get it. We're plugging here. So we got VCM has to be larger than VDD minus VOV5 minus VGS1. So the next step is that we need to find what VGS1 is. Because VGS1 has to be larger than, okay, let's go on stage. For any transistor, we know that the condition is VGS has to be larger than VT. For PMOS, we can use again absolute value, and VDS has to be larger than. So VDS again use absolute value has to be larger than VGS absolute value minus VTO. In this case, we got ATN, VTP. Well, actually, for Q1, yes, it's VTP absolute value. So the difference between VGS minus VTP is called VOV. So in this case, VOV1, again, we use absolute value. It's going to be VGS minus VTP. So and then from here, we have VGS1. Again, we call VGS1. VTP equal to VOV1 plus VTP. So that's what we got. Now, if you go back to the previous slide, we already have this equation here. VCM has to be larger than VDD minus VOV minus VGS1. So therefore, we're going to say, okay, so VCM has to be larger than VDD minus VOV1 VOV5 minus VGS1. And VGS1, we already know that is equal to VOV1 plus this. So we got VDD minus VOV5 minus VOV1, and then minus VTP. So here we got our upper limit. We got our upper limit. The next step is that we want to look at the lower limit. So let's again look at lower limit. So for lower limit, we have to make sure that this Q1 and Q2, these two transistors must be a saturation. So Q1 and Q2 must be in saturation. So if we make this in saturation, which means that VCM, if you look at this, which means, again, I want to rewrite. Remember, VOV, this is a PMOS. So we're going to write VOV in the form of absolute value. That's VOV, right? So, I mean, we know that VDS has to be larger than VOV. Therefore, our plugging VOV use this equation here, and then we set VOV equal to VGS. Here is VGS1 minus VTP. So therefore, VGS1, let's say VGS3. Okay. So now also, okay. So now let's go ahead and figure out what is the voltage over here. So apparently, if you look at here, it's VDS3 equal to VGS3 because the gate and drain are connected. So we have VDS3 equal to VGS3 equal to minus VSS minus VSS. Well, hold on, sorry. Yes. And VGS3 has to be larger than VGS3 has to be larger than VDS3. So VDS3 has to be larger than here. Oh, well, 3 is a MOS. So we for MOS we don't have to use absolute value, but so I'm gonna, because they're positive. For PMOS it's obviously negative. That's why we use the absolute value. But for MOS it's always positive. So we don't have to use. Has to be larger than VTN. Let's call it VTN. For this Q3 or Q3 in saturation. So since VDS3 has to be, now VDS3 equal to what is VDS3? Now VDS3 is equal to minus, let's call this here VD3. So VDS3 is going to be, or in other sense that I'm going to write this way. In fact, our VD3 equal to minus VSS plus VDS3, and VDS3 has to be larger than VTN, so VDS3 has to be, so VD3 has to be larger than minus VSS plus VTN. So this, we got this VD3 over here. Now once VD3 is fine, and we can see that VD3. Let me rewrite this equation on the next slide. So VD3 has to be larger than minus VSS plus VTN. But we have to identify the relation between VD3 and VCM. So we're going to look at this relations. VDS3, we owe, oh no, actually I missed something. So VDS, VG, let me see. So VDS3 has the VOV, VGS1, VTP, and VDS3 has to be larger. Oh, I'm sorry, I made a mistake here. So let me actually got this erased. This is wrong. It has to be larger than. It has to be VDS3 has to be larger than VOV3. Therefore, VOV3, because VOV3 is equal to and then okay. So VOV3 equal to VGS3 minus VTN. So therefore, we have VGS3. We have to erase this one. It's going to be minus VSS plus VGS3, then minus VTN. Okay. And then from here, so we minus VSS plus VG3 plus minus VT. Okay. So plus VGS VOV3 equal to yes, which one? VOV3. This should be a mistake. So VTN, VGS3, VDS3 larger than VOV3 minus VSS plus VOV3 plus VOV3 and plus VTN. Let me see. There's apparently a mistake somewhere I just made. Sorry about that. VD3 equal to minus V33 minus VDS3. VDS3 minus plus VD3. VDS3 equal to VGS3. VD3 to equal VGS3. Oh, so VGS3 equal to VGS3 equal to VOV3 plus VTN. Okay, so plus VTN. So we have plus VTN. So it should be plus VTN. But VOV3. So here it's a little bit tricky in identifying these numbers because I can rewrite this in the next slide. So VDS3 can be replaced by VGS3, so which means it's VOV3 plus VTN. Okay, so now I got it right. So this VDS3 has to be larger than this, and VDS3 equal to the VDS3 equal to VCM, and we have VDS1 PMOS larger than VOV1, which equal to VGS minus VTP. So VOV is VGS minus TP. Okay, that's correct. And then so VDS1 equal to VS1 minus VD1, and it has to be larger than VS1 minus VCM minus VTP1. So VTP1. Okay. Now the reason we can do this because this transistor, let me redraw the transistor of Q1. So Q1 is like this. So this S, this D, this VCM. So if you can see here, if you from this circuit, you can know that VDS or VDS absolute value equal to VS minus VD, right? So here you got this. And also from here you have VGS absolute value equal to VS minus VG, which is VCM. So here we plug in these two equations back to this equation, we have VS1 cancel. So we have VCM is negative. We move on the left side, much larger than VD1 minus VTP. And VD1 is already find out, so which equal to minus VD1. Basically, this is equal to VD3. VD3, you see, let me go back one slide. So VD3 and VD1 are the same. It's here. So basically, if you draw the circuit, this is VD3. The circuit over here, this is 1. And actually, 3 is here. See, this is D of 3. So D1 and D3, they're together. So this is the same. VD1 and V3 equal to the same. And it's the same point. So therefore, we have VSS minus VSS plus VOV3 plus VTN, and then minus VTP. Okay, so we get this lower bound. CM has to be larger than this, and we also get the upper bound. So now we can write the input range is VCM has to be larger than minus VSS. That's the equation here. Plus VOV3, and this is make this a little bit better. Has to be larger than V minus SS plus VOV3, and then we have plus VTN, and then minus VTP. Again, absolute value. And also this lower bound. This lower bound for the CM. And then we also already derived the upper bound. We go back to the slide. We have the upper bound is here. So VDD minus VO5 minus VO1 minus VTP. So basically, we have VDD minus VOV5 absolute value, and then minus VO1 absolute value, because they are the PMOS, VOV1, and then minus VTP. So that's the upper bound. So if you look at this equation, it's interesting. It's not symmetrical. The reason is typically you can have VTP approximately equal to VTN. The threshold voltage of PMOS and NMOS are similarly the same. Therefore, if you can simplify this one, because you have VTP and VTN here on the right hand, so therefore you have VSS plus VOV3 as a lower bound, but at the upper bound you have VDD minus VOV5, but minus 2 times VTN, because VTP again similar as VTN, so therefore you have 2 times. So therefore the lower bound is much wider than the upper bound. The upper bound is done by 2 times VTP. The upper bound is only deducted by VOV3. So this is what we have for the up and lower bound. And therefore, we have this input common mode range. So you remember the reason we talk about it, the common mode range, is because we want to make sure if our input is too big and the system will not work. All the transistors have to be in saturation in order for the system to work, right? So therefore, we want to make sure that our common mode input is in a certain range. So, like given sometimes your input can be like this, but sometimes it can be like this, which means you have a VCM plus VID. So if you have VID at the central, you're absolutely fine, as long as the input is not big enough that your output is not saturated, it's fine. But this value, this top value and bottom value cannot be larger than VCM max and VCM min. So max and the bottom is VCM min. But if your input contains common mode input and differential input, therefore your range will be limited by here. So therefore you cannot be too high because your up bound cannot be more than VCM max, but your lower bound is okay because it's never going to be reach the lower bound. Or sometimes you might have an input like this, and you're fine too. But sometimes you might have an input simply like this, just the common mode. So for common mode, this one has to be less than VCM max. Or if you have an input like this, it has to be larger than VCM max, minimum. So your input is always be 10. So your input can be anywhere between this one. It's fine. Anywhere in between, any DC or AC, whatever, it will be fine. Okay. So now we got the input range. I think we need to have look at the. Oh, actually, I used the wrong slide for the output range. So let me add another slide so that I can. Well, let me move this out. Okay, I don't know how to delete this. Good. Well, here I want to change. This will be input range. We're talking about on this slide, we did talk about the lower limit. So now we need to talk about output range. So for output range is relatively simple because we just need to look at what is VO in terms of range. Now we have Q7 and Q6. So for upper bound and Q7 has to be in saturation. Q7 in saturation, which means VDS7 absolute value, again, this is PMOS, has to be larger than VOV7. Again, absolute value, but VDS7 equal to VDD minus VO, minus VO. So therefore, VO has to be, now we move this one on that side, VO is less than, or actually, we can do it very simply, in a simple way. You can say VO equal to VD7, no, VO equal to VDD, we move VO on that side and VD7 on the left side, we got VDD minus VD7, again, VDS. But because VDS7 has to be larger than VOV7, so we got VDD has to be less than now because this again let me get this much better. Has to be the VDS7, but VDS7 has to be larger than VOV7. So therefore, we have VO has to be less than VDD minus VOV7. So that's our upper bound. And for lower bound, VQ6 has to be in saturation. So for lower bound, Q6 has to be a saturation. For Q6 to be say it's NMOS, so we can say that VDS6 has to be larger than VOV6, and VOV6 is equal to well, VDS6 equal to VDS6 is here equal to VDS6 equal to VO minus VSS. Okay, so minus actually minus VSS. So equal to VO plus VSS. And then now we plug in this one to here. We got VO equal to VO plus, so VO equal to VDS6 minus VSS, and VO6 is VO6, plugging VO6 here, VOV6 minus VSS. So we got our lower bound. Therefore, we can write down VO, I write down here, so it has to be larger than V minus VSS plus VOV6, and then less than VDD minus VOV7 here. So as you can see here, your output range is very big. It's only short of VOV6 and VOV7. So if VOV is small, and your output range will be big. If VO6 and VOV7 is 0, actually your output is so-called rail to rail. So I just give you the concept. So if VOV6 equal to 0 and VOV7 equal to 0, then your output is minus VSS less than VDD, and this is called rail to real. But this is a condition that your VOV6 and VOV7 is 0. But in general, we can increase the range by reducing the VOV of the last stage of your amplifier, not before the power amplifiers. The power amplifiers is a different stuff. So now I want to go ahead to look at what we can do with the gain. So we already have the input and output range, but we want to also look at, what is the gain of the circuit? Now, for the gain of the circuit, all we need to do is to draw the small signal circuit. And if you remember, I already look at, like, this one is equivalent to a current source, right? Current source. Okay. So Q6 is a current source, which is equivalent to this. And here is equivalent to a current source in series with a resistor. And this one also is a current source with a resistor. And here is a current source with a resistor. And this one here and here, we can do the small signal model. So from the signal model, from the first stage, we have input, VID, and then you have Q1, you have current source, and you have its own internal resistance, RO1, and also you have RO3 connect to the drain, right? So that's your first stage. And the other one is your Q2, so this is Q1, and that's Q2, you have this RO4, and you have RO2, its own resistance, and you have its own amplified current. And over here, you have your input, right? So your input is basically connected. And your output, your input here is so your VID is connected over here. Because this one has nowhere to go, so therefore we only measure VO1 here. If you do this circuit, you can easily identify that this is GM1 times VID. Okay, and then here will be 1/2 like VID, and this here will be GM1 times GM2 times 1/2 VID, right? And then you can easily find that the VO1 is really just minus GM1 or GM2 times RO1 in parallel with RO3. And also equal to Y GM2 times RO2 in parallel with RO3. So that's your first stage, very simple. And then for your second stage, we can draw the equivalent circuit again. For your Q6 MOS, it's easy. So you have VO1 coming in. Now, for now, forget about this VC. So, and then you have its own resistance RO6. And at the drain, you see, you have RO7. So therefore, at the drain, you also have RO7. And the output is get at VO over here. So this is GM6 times VO1. So therefore, you have your output is equal to GM6 times VO1, and then times RO6 in parallel with RO7. Okay, so that where you have this VO, here I forgot this VID or VI input, and here you have VO1. So therefore, from here, we can get our two gains. So your first stage gain, that's called GM2, RO2, RO4. That's your first stage gain. And your second stage gain equal to GM6, RO6 in parallel with RO7. And your total gain will be A1 times A2 equal to GM2 times GM6 times RO2 in parallel with RO4, and then times RO6 RO6 in parallel with RO7. So that's your gain. If you notice here, GM2 and GM6 can be basically typical just a number in single digits or in the tens. But this resistance, let's call this R1, let's call this R2. So R1 and R2 are generally in the kilo ohms range, tens of kilo ohms. So therefore, your A will typically in the range of in the hundreds to it's typically in this range. Depending on the design, you can have a fairly large gain. So even though this is two-stage, your gain can be fairly large. So therefore, we have the gain derived, and we can actually now draw the equivalent circuit to look at the actual derive the whole like the gain in terms of function. Now that middle band gain, as I wrote in the previous slide, is this one here. So I want to rewrite it here. So it's going to be GM2 times GM6 and times R1 times R2. Okay. So we know that. How do you calculate GM1? You might already forget, but GM1 and GM2 can be calculated using its biasing current. So it's biasing current divided by VOV. So like this is how you calculate this, right? So it's a PMOS, again, if it's PMOS, use absolute value. And this is equal to 2 times ID2 divided by VOV2. And we know that ID1, ID2 equal to half of the biasing current. Remember, the biasing current is from the Q5, and it's divided by half for each transistor. So therefore, that 2 and 2 would cancel. We got this I over VOV2. That's what we get for GM2. Now for GM4, for GM6, you can do the same thing, which means it's going to be 2 times I D6 over VOV6. And it's here, ID6 is equal to I. That's the same current. So therefore, you get 2I divided by VOV6. That's GM6. And we can also calculate R1 and R2. So R1 equal to RO2 in parallel with RO4. Now, remember how we calculate RO2 and RO4? That's like early resistance is equal to this early voltage for PMOS with absolute value divided by its ID. Well, ID1 or ID2 is half of current, so we got VA2 divided by half I, which equal to 2 times VA2 divided by I. And similarly, we can get VO RO4 would equal to 2 times VO VA4, which is early voltage divided by I. And for RO6 and RO7, for RO6 and RO7, we can use the same equations or similar equation. RO6 equal to again it's VA6 over absolute value over I. D6, ID6 is I, so we got VA6 over I instead. The previous was 2I. Okay. So and then RO7, we can get it also VA7 similarly divided by I. So we got all these equations. So now I can write A1 and A2. We can really just talk about so we know that this GM, again, I write again, we have this A equal to A1 times A2 equal to GM1 times GM2 times R1 and R2 times R1 times R2, okay? This times. And R1 equal to RO1 or RO2 over RO4, which you can also write as RO1 equals RO3. That's the same thing, okay? But RO2 and RO4 we already find out. So now we can put RO2 and RO1, RO4 in parallel. RO2 and RO4, which is going to be, this is going to be 2 times I. Okay. So it's going to be 2 times VA 2 over I in parallel with 2 times VA4 over I. VA4 is a MOS, so you don't have to use absolute value, but here we can simply do that. Now, when this thing's in parallel, you know what happened, right? You simply and then here you can multiply I at the top, and then you can divide 2 over here. You can get VA1, VA2 plus VA4. So this is what you get for R1. And similarly, you can get R2, and it's going to be I over VA6 plus VA. Oh, I made a mistake. Sorry. That's why it's not correct. This is all right. I have to use the when you have this in parallel, which basically you write okay. Let me write here. So when you have R1 and R2 in parallel, or whatever, this RA and RB in parallel, this is equal to 1 over RA plus 1 over RB over 1. So here we have to write I over VA2 plus I over 2 times VA4 and equal to 1. So I have to write down that way. So now we can multiply VA1 and VA2 there. But simply what I do is I'll move this I on top. So you got 2 over I over 1 over VA1, VA2 plus 1 over VA4. So similarly, we can get R2 equal to I, because that 2 is gone. I 1 over VA6 plus 1 over VA7. Okay. So that's R1, R2. So when you go to this equation to get A, we can simply do that. We can plug in this one. Now, also remember, we already have GM6 also derived and GM2 derived. So we can plug in all these numbers to get this one here. So we will get, add another slide here. Okay. So now we can plug in this A to get, again, I want to write this GM1, GM2 times R1, R2, and we can plug in all these numbers. Now we have GM1 derived already. Let me check GM1, GM6, sorry, GM2 and GM6. With I over V2, and this 2I over V6. Okay, so this is GM2, GM6. So this is I over V2 times 2I over V6, and then times R1, R2. So R1 is given like this. Is I 2OI times divided by 1 over VA2 plus 1 over VA4, and then times I over 1 over VA4 plus 1 over VA6. Okay, so we got this number. As you can see here, this I is going to cancel, and this 2, why is the 2 not canceling? That 2 is supposed to get 2I, 2 is that, so it should be, okay. So this looks like this 2 will not cancel, we'll get 4. So I cancel, so we will get this equation eventually to be, let me see, what do I get? Yeah, so this eventually going to be 4 times. So it's going to be 4 times VOV2 times VOV6, and times this 2 numbers here, times this one here is 1 over VA2 plus 4. VA6, and we have 7. So VA6 plus VO7. This is kind of a pretty complex equation, but the idea that over here you can see the total gain, even though we divide it by a number of cents, so eventually it's inversely proportional to VO V2, VO6, right? So it's inversely proportional. And also it's inversely proportional to VA2 over 1 plus VA4. And this inversely proportional, which means if VA2 is larger, it gives you a smaller number at the in the denominator. So therefore, we basically can say that the sense is related. It's not purely proportional, but it's really almost it's real. Yeah, we can do that. It's okay. So if this is really proportional to A6 and A7. So which means if we make smaller VOV and a larger VA will result in larger A, larger gain. So that's this basically goes back to, okay, you want to design your amplifier, you want a larger gain. What you can do is you design a smaller VOV and a larger VA. So then we get this really that gain. So in fact, before I go to the frequency response, I want to here didn't get enough slides. I want to go also to talk about input and output resistance. So let's look at input resistance. Now, input resistance refer to the first stage or the differential stage. If you look at the differential stage, that we draw the circuit like this, right? And our input VCM or VI is over here. And there's nothing connected, right? There's nothing connected to the between the input terminal and output. So therefore, your Rin is equal to infinity. I mean, virtually infinity. So this is great. So, but if this is BJT, if this whole thing is replaced by MOSFET, replaced by BJT, you would have an equivalent resistance of this. You will have VI plus VCM, and you will have your R pi. And since this is differential stage, you have another circuit, so therefore your input resistance will be something like R pi times 2. Because your input is connected, not actually your input is not connected to here. Your input is connected to another circuit on the other hand. So this is your input here, but then you also have another one here, right? So you have input, and then there you have input is to R pi. And also we're going to look at output resistance. For the output resistance, we need to look at the output circuit. The output is Q6. So the Q6 have RO6, RO7. And suppose you don't have, here is the ground. So this is GM6 times VO1 and your VO. So when you find output resistance, you would short the input. So basically means you would short input. If you short input, VO1 is, so you short input, which means input VO1, you put it 0. So therefore, GM times V0 is equal to 0, which means open. So really, you have this circuit over here is open circuit. So basically, your equivalent circuit becomes RO6, RO7, your VO. And you look in here, your output equal to RO6 in parallel with RO7. So this can be fairly large. But of course, this is not as large as your emitter follower or source follower, but this is a common source amplifier for the second stage. So therefore, even though the resistance is fairly large, but it's not that large. But it's good enough. If you want to increase the output resistance, you can actually add a third stage as emitter follower, which is the gain almost 1, so the gain doesn't change for the whole thing, but the output resistance increases to almost infinity, like in the megohms range. So it's really good. But of course, if we the other thing that, if in the future we have some load connected, the whole thing is going to change, which means if you have your load connected, so if you have a load resistance connected, and your output resistance would really depend on substrate. So your output resistance RO will be RO6 in parallel with RO7 in parallel with RL. And typically this RL is much smaller than RO6 and RO7. So that means that regardless of what your second stage is, regardless of the output resistance, your output resistance will be eventually determined by your real load resistance, right? So this is what we're looking at for the output circuit. Now, in the next step, we're going to analyze the Frank response. And when we analyze the Frank response, we're going to talk about the function of CC. And in addition, we might also add a resistance for RL and a resistance for CL. Now, often the time, this RL, it doesn't have to be there. So if it's not there, it's infinity. But CL is definitely there. And the CL, it typically can be fairly large. And so it's going to impact the Frank response. And in order to talk about Frank response, of course, we need to just look at really just this two stages and here. So basically, if I redraw this, what we're going to be looking at is just the current source and the current mirror, they generally will not impact the output, the Frank response. With this one here, just make it clear that what we're looking at next time is the circuit over here. This is our Frank response circuit. And we're going to redraw the circuit. Of course, the resistance, like this one here, is going to be included, resistance here included, and the resistance will be included. And when we include this resistance, we can draw the small signal equivalent circuit very easily. So this is the input side, and this is output side. We already drew it before. So the input side, we only represent it with the half circuit. And for the Q6, here we use Q2. And you look at between Q2 and Q6, there's capacitor CC. So that's this capacitor over here. And C1 is C1 basically looks like it's here. So it's a equivalent circuit of the whole impedance of Q1 and the impedance of Q2. So here you see we have C1 and we have C2. And here also later on, we're going to also add a CL over here. So we're going to write this equation, and we're going to derive the Frank response in our next lecture. And so I think our time is almost over. Yeah. So I'm going to stop here. And on Wednesday, we're going to look at the Frank response. We're going to start from this slide, clean. And as I mentioned, I'll just repeat the next lecture, which is Wednesday. We're going to talk about Frank response. We're probably going to spend, we'll probably spend the whole lecture to talk about the next few subsections up to 13.1.6. So it's up to 13.1.6. And we're going to stop here. So we're not going to talk anything about further like anything else. Yeah. So and then again on next week on Monday we'll have a review. So hopefully it's in person on Monday. You should be there because it's very important to understand what you have learned, connect the dots, and also understand what will be in the final and what my expectations are for the final. So one more thing I want to remind you that there's a course survey, which is evaluation of my teaching and the course material and everything else. So you should get an email notification from Canvas, and then you can go ahead do the survey. Now, survey needs to be done before the final exam, which should be done by this next Wednesday. And not this Wednesday, but next Wednesday, you should get everything done. So therefore, please do it. And if you have any feedback, what you feel good about it, what you feel not good about it, anything else you want to help us to improve the class, you're welcome to give us a feedback. With that, thank you for your time, and I will see you on Wednesday, again, virtually. Wednesday lecture will be also online, and I'll see you Wednesday virtually, and I'll see you on next Monday in person. Bye-bye. Any questions? Yes. Okay. Don't see. If you can type a chat or you can ask questions if you want, but otherwise feel free to log off. I'll wait a little bit until everybody logs off from now on.